Hey now, living environment fans, it's time for our daily Bellringer. We made it to Tuesday of this week. Remember, the quarter ends at the end of this week, so it's your last chance to get everything put together and turned in. Right? We've got one more lab assignment, the embryology lab, to add to our lab checklist for this quarter, and then it's on to the fourth quarter. So some of you need to get shaken. Like, I expect a big fourth quarter in terms of labs, because you do not want to not be able to sit for the regents. Okay? What that means is you need to have the lab credits. If you don't have the lab credits, you might even pass my class, but you're not going to be able to sit for the regents. And then you have to take a class where you can get those credits. I don't know where you're going to take that class. Take living environment again next year? It's not offered during summer school. So you got to figure that out. You got to get yourself there. Remember, that's on you. I get lots of time and lots of minutes, so there's no excuse really. Anyway, we'll talk a little bit more about labs and stuff in class, and we'll also talk about other weird things. Like, we've talked about embryos, and we've talked about like homologous structures. We're going to talk about vestiges and things like that as well. So let's do today's bell ring. All right. Hey now. Mr. Kovacs class. It's Mr. Kovacs class. You might learn a ton. It's Mr. Kovacs class.
He's interesting too.
It's Mr. Kovacs class.
And he's super cool.
It's Mr. Kovacs class. Met my friend Vlad yesterday, Vlad the Impaler, who, although his skeleton looks just like ours, just with longer bones and things like that, he's not one of us, right? We said that when you put all that stuff back on him, you get a bat. Okay, but the point we're trying to make is that bats, people, whales, horses, we all have the same plan for building our bones, bone structure. We have the same bones in the same order, in the same places. The only difference, of course, is relative size. And then some of us use those bones for different things. Vlad uses his bones in his hand to fly. A whale would use them to swim, etc., etc. Right? We call those homologous structures. That's evidence of common ancestry. Why is it evidence? Because where do you get the plan to build your bones? You get that in your DNA. You get that in your genes. Where do you get your genes from? Your parents. Where did they get them from? Their parents. Where did they get them from? Their parents. Back and forth. So if you have the same genes as a horse, eventually you go back far enough, there was a parent who was the parent of both you and the horse. That parent was neither a you or a horse, but a common ancestor. Common thing we see are what we call vestiges, which are the word vestigial means kind of left over, right? Vestiges, which are examples of, again, of common ancestry. Like the whale's hips is a classic example of a vestige. So this whale has the genes to make hip bones and a little bit of a leg bone. Where did it get the genes to make those bones? From its parents. Where did they get those genes? From their parents, from their parents, their parents. The idea is somewhere along the line in the lineage of this whale, there was a parent who had legs, who needed leg bones. And then over time, the need for leg bones decreased, and therefore they were kind of lost. But we still have leftover remains, vestiges. And actually, the fossil record supports this. If you look at whale, you saw that yesterday in our Edpuzzle video. There are plenty of intermediate whale fossils or ancestors of whales who have legs, and it's only modern whales that don't have legs. We see this with the appendix, right, is a classic example of a human vestige. Right? Lots of animals have appendices, but like humans, a very small one that you can lose and you don't have to replace. That's not true for a koala. A koala can't live without its appendix. A kangaroo can't live without its appendix. A rabbit can't live without its appendix. It's not like the organ itself doesn't do anything. Just in our species, it no longer needed. It's a vestige, vestigial structure. Wisdom teeth, another example I gave you, I think, yesterday of a vestige, right? In our species, some of us grow these extra teeth, this third set of teeth, but we don't need them, right? And oftentimes they have to be removed, right? And we live just fine without them. They're like leftovers, unnecessary. Where do we get them from? Well, we have genes to make them, which we inherited from our parents, from their parents, and so on and so forth. Which means somewhere down the line we had an ancestor who needed those teeth. I don't know, maybe like before fluoride and dentistry and stuff, most human type organisms would have lost teeth. So a new one grows in and shifts everything over so that you have a complete set of teeth. I don't know, that's just speculation, right? But those are called vestiges. And of course, the greatest piece of evidence of common ancestry is in our DNA. I mean, if you look at something as simple as hemoglobin, you'll see that the difference between species to make hemoglobin in terms of their genome is like just a few base pairs, A's, T's, C's, and G's. And the fewer base pairs you have different, the more closely related you are. Right? We call this a cladogram, which shows how closely related things are. Right? And so a human being and a macaque are only different by 8 base pairs in their hemoglobin molecule, while they're different by 32 base pairs with the dog, which means humans are more closely related or have a more recent common ancestor with macaques than they do with dogs. All right, hopefully that makes sense to you as we talk about pieces of evidence for common ancestry. Right, so the evidence is pretty overwhelming of common ancestry, that you have genes are passed from parents to offspring over generations and over time. And if you can have enough time, you realize that genes in populations can change in one population versus another population, and you get different species. We're going to start talking about the man who came up with that first idea, or that idea first, and probably became one of the most famous people of all time, not just scientists, for coming up with this, a man named Charles Darwin. And so that's what we're going to talk about the rest of this week.